So good afternoon, good evening, or good morning, everyone, and thank you for being here today. Today, we have the pleasure to welcome Dr. James Muirhead from the University of Auckland, and he's going to talk about continental rifting with all the couplings with volatile, magma, and climate. So James, the floor is yours.
Great, thank you, Catherine, and thank you for this invitation to speak on some of the work I've been doing with continental rifting. So some of the work I'm actually going to show you, which now when I'm thinking about it, does feel actually a bit old, which makes me feel a bit old, and that's because some of the stuff I'm going to present is actually work that I was doing with others during my PhD, looking at the role of magma and volatiles in continental rift development. And so we'll start off with that, and then we'll start to then look at some newer work that I've been collaborating with people on, where we're now examining also the role that climate may play in helping to assist in rift basin development, particularly in East Africa. Cool. So to do this, we are looking at the East African rift system. Before I want to begin on this, I just want to point out that a lot of the data and the ideas that I'll be presenting have come about from the hard work of friends and collaborators as well. This includes my PhD advisor, Simon Cadenhorn. Cindy Ebinger has provided a lot of advice and mentorship, particularly during my PhD years. Tobias Fischer, shown here, has been sort of a really great and generous ally and collaborator. As Hyunwoo Lee, shown over here. Then there's my postdoc advisor, Christopher Scholes. Miriam Rees has worked with me more recently in Tanzania, and though I don't actually have time to show the results from the work I've done with her, though it is actually really relevant. And then lastly, Tyrone Rooney has been working with me recently for some of the stuff you'll see for the Lake Turkana Rift. So we're going to look at the evolution of continental rifts, and we can consider some broad and fundamental questions related to continental rifting. How is continental breakup initiated, and how do continental rifts develop and evolve to the ocean spreading centers that we see today? So for reference, I've included some examples of active continental rifts on Earth today. This includes the Baikal Rift in Russia, the Rio Grande Rift in the US, Mexico, and then also the East African Rift, which is the focus of our presentation. So the East African Rift forms the southern arm of a triple junction between the Red Sea and Gulf of Aden rifts, and it's classically divided into these western and eastern branches, where the eastern branch is thought to be the type example of magma-assisted rifting, and the western branch is thought to be comparatively magma poor. So these differences in the role of magmatism are emphasized here in this figure, showing the distribution of rift volcanism in East Africa. What we see is we have significant volcanism in the eastern branch versus the western branch, and hence magmatism is more involved in the rifting process in the east. Right here shows us a cross-section through a seismic tomography model below the rift from Malebo and Nyblade. So areas of enormously slow S-wave speed are shown in red, and they indicate enormously hot mantle that'll be prone to melting. And from these data, we can see that we have higher magmatic input in the eastern branch and less magma in the west. So things kicked off in East Africa about 30 million years ago with the eruption of the Ethiopian flood basalt lavas. Rifting then initiated somewhere around about 45 to 30 million years ago in some discrete depot centers. And since this time, the rift has progressively migrated southwards. And this is also illustrated in the ages of the earliest rift lavas in different sectors of the eastern branch. And this shows us as we go from north to south, the rift progressively gets younger. And this younging of the rift is fortuitous because it provides us with the opportunity to investigate rift basin architecture at different stages of rift evolution to get an idea of how rifts evolve through time. So this idea was first explored by Hayward and Ebinger, and they looked at the architecture of Ethiopian sectors of the rift. And what they found was, as you go from south to north, or as you go from younger to older, the location of strain migrates from the rift borders towards the rift center, and then rifting becomes progressively more magmatic. So based on this study and many others in the eastern branch of the East African Rift, we have a simplified conceptual model for the evolution of rift basins, particularly in the eastern branch. So in the first about 5 million years, strain is focused on the rift borders and what we call border faults. Then between about 5 and 10 million years, it migrates into the rift center, into inter-rift fault populations. And then from about 10 to 20 million years, we start to develop nascent seafloor spreading ridges, or what we call magmatic segments. And then by about 20 million years or older, seafloor spreading starts to fully kick in, and we're building a new oceanic lithosphere. In this presentation, we'll be exploring and testing this model here for rift evolution. In particular, we will focus on how fault system development is impacted by magma, volatiles, and climate. And we're going to do this in 3 parts. In the first part, we'll look at early stage fault development and whether it's impacted by magmatic volatile release. In the second part, we'll look at fault development during the establishment of these magmatic segments. And then lastly, we'll finish by exploring how fault system behavior might actually be impacted by climate changes in the East African Rift. So for our first part, we'll explore how magmatic volatiles interact with fault systems in early stage continental rifts. And this part is primarily based on work from these papers here that were published in 2016 and 2017. So just one more refresher for our conceptual model for how rifts evolve in the Eastern Rift Branch. At first, strain is focused on the rift borders, what we call border faults. It then migrates into the rift center, into inter-rift faults, and then rifting becomes progressively more magmatic in this model. And for this part, we are focusing specifically on this transition here, the transition from border faulting to inter-rift faulting. And we're going to ask 2 questions. When does this transition to inter-rift faulting occur? And is this transition linked with magmatic volatile release? So seeing as we're going to be looking at magmatic volatiles or mantle volatiles, it's nice to actually start with a conceptual picture of how these volatiles may be mobilized during continental rifting. So in this example, we have melting of a asthenosphere and incorporation of mantle volatiles into magmas. These magmas then ascend as dikes and intrude into the crust, where they will cool, crystallize, and then begin to release these volatiles into fault and fracture networks, forming in our extending crust and lithosphere. So if mantle volatiles are actually driving strain localization, we would need to see the following observations in an active continental rift. We would need to see evidence for magma entering the crust. We would need to see evidence for the release of mantle volatiles along faults. And then lastly, we need to see evidence that these mantle volatiles are helping to focus fault-related strain. And we will address these 3 questions here in this first part. And I'm going to provide a mix of geophysical, geochemical, and structural geologic observations to support these 3 key hypotheses. To do this, we are going to look at the Magadi and Natron basins at the border of Tanzania and Kenya shown here. These basins are 3 and 7 million years old, So we're looking at early stage rifting. And to give you an idea of the crustal structure here, I'm going to show some seismicity and geophysical data. So in 2013 and 2014, Cindy Ebinger and others set up the 32-station Crafty seismic array, and the stations for this array are shown here as these purple triangles. During this time, more than 3,000 earthquakes were detected on this array, and based on these data, Steve Varuka put together a 3D seismic tomography model for the crust region. So here we have a cross-section through his tomography model from west to east. Areas in red show us anomalously low S-wave velocities. And in general, we see we have low S-wave speeds below the neutron rift. These shallow, low S-wave speeds might represent the basin-filled sediments and volcanics in the neutron basin. And these low S-wave velocities in the lower crust could potentially represent the presence of magma bodies. And perhaps more interestingly yet, surrounding this crustal low velocity zone are swarms of mid to lower crustal seismicity, which might signify magma intrusions or magmatic volatiles being released along fault and fraction networks. So to test whether magmatic volatiles are actually ascending along fault networks, we adopted the CO2 accumulation chamber method shown here. With this device, we can measure CO2 coming up diffusely from the ground and into our chamber. We draw that gas up into our gas analyzer, which has an infrared analyzer, which can measure the concentration of CO2 in our chamber. We can then look at how the concentration of CO2 changes through time to get a flux of CO2 coming up from the ground. We can then measure CO2 flux in and around fault structures to see if there's a structural control on the migration of CO2. And then we can actually sample these gases for isotopic analyses to understand the source of the CO2. So here we have an example of our CO2 flux data. This is a transect through a faulted graben in the Magadi Basin. The points in red here relate to our CO2 flux values, which you can see on the y-axis. And what we observe in the neutron and Magadi basins is that we get high CO2 flux in the vicinity of faults. And this suggests that these faults act as permeable pathways for the ascent of CO2. Like I mentioned, we also sample these gases and analyze their isotopes to examine the volatile source. So here we have our carbon isotope data for neutron and Magadi. We have CO2 concentration on the x-axis with high concentrations to the left. We have delta 13 carbon on the y-axis with high carbon 13 at the top here. We also have values for possible N members. We've got values for air, biogenic CO2, and mantle carbon. And when we interpret this plot, we need to remember that our samples capture both air and the carbon source. And our data fit really nicely on a mixing line between air and mantle carbon. And this mantle carbon signature suggests that the CO2 is sourced probably from deep crustal magma bodies. So in all, this suggests we have magmatic CO2 degassing from lower crustal magma bodies along rift-wide faults. So this brings us to our final question. Our mantle volatiles are focusing our fault strain. So we're going to ask where fault strain is focused within our rift basins. And we're going to estimate this in the following way. First, we'll calculate the total extension in our intra-rift fault population. We will then use the ages of these faults to get a time-averaged extension rate. We're going to compare our extension rates for the intra-rift faults with the extension rates for the entire basin based on GPS modeling from SARIA 2014. And by comparing these two values, we're going to get an estimate of the extension rate along our border faults. We'll then see where the greatest amount of strain is focused, and we'll ask ourselves whether there is some relationship between high strain and the release of mantle volatiles. So for the study, we're still focusing on the Natron and Magadi basins. And just remember, the Natron basin is 3 million years old and the Magadi basin is 7 million years old. So if we compare where fault strain is located in these basins, then we can infer how the location of strain may evolve over the course of rift evolution between 3 and 7 million years. So for the study, I mapped out all the faults in the area using aerial photos. We can see this fault map on the right. Intra-rift faults are shown here as these red lines, and the border faults are these black lines, and they bound at basins. These fault maps were ground truth during 3 field investigations. And then lastly, we measured throws on these faults using the 30-meter SRTM digital elevation model. In order to estimate the total strain accrued in the intra-rift fault population, we use the method of Schultz and Cowie 1990. Essentially, what we do with this method is we sum the total amount of extensional strain for an entire fault population based on the displacement, length, and depth extent of our faults, and then we multiply this by the inverse of the faulted volume, which gives us horizontal extensional strain, and that's in our intra-rift faults only. To convert these extension values to extension rates, we sampled the lavas dissected by these faults, and we dated these lavas using argon dating, and we use these dates to get time averaged extension rates. So here we have the results from our extension calculations for the intra-rift faults. We have 2 strain transects, one through the Magadi basin shown here, and one through the Natron basin. We have distance along our axis, along the transect on the x-axis, and percent extension on the y-axis. And these gray points here that you see represent the percent extension in each of these little boxes along our transect. And what you can hopefully see immediately from these results is we're accumulating a lot more extension in the intra-rift faults in the Magadi basin compared to the Natron basin. Lastly, we dated the lavas that these faults dissect to calculate extension rates for our fault populations. And these are the results that we got. So in the Magadi basin, the intra-rift faults are accommodating significantly more extension than the Natron basin at 1.6 millimeters per year compared to 0.5. We also compared these values to the extension rates estimated for the entire basin based on GPS modeling to get an estimate of the extension rates on our border faults. So subtracting 1.6 millimeters per year from this 2 millimeters per year, we get an estimated extension rate on the border fault of 1.4 millimeters per year in Magadi. Taking the same approach in the Natron basin, we have an extension rate, time average extension rate of 1.3 millimeters per year in the Natron border fault. So if this exercise was somewhat hard to follow, all you need to actually remember from it is that the highest strain in the Magadi basin is focused in the intra-rift faults, and the highest strain in the Natron basin is focused along our border faults. We know the ages of these basins. The Magadi basin is 7 million years old. Natron basin is 3 million years old. So based on these observations, we are suggesting that we get a transition from border fault dominated strain accommodation to intra-rift faulting somewhere between about 3 and 7 million years after rift initiation. And this brings us to our final question. Is there a relationship with strain and fluid flow? So keep these locations of high strain in mind, because on the next slide, I'm going to show you the locations of springs in our study region. So our yellow stars here are showing us the locations of springs in the region. So in the Magadi basin, fluids are rising up through the center of the rift where we have the highest extensional strain. In the Natron basin, they rise up along the rift borders, again where we have the highest strain. This photo here shows us an image of these springs. They run fault parallel and they manifest at the base of fault scarps. So we have a structural control on the flow of these fluids. We also sampled these springs for helium isotope analyses, and we find that they are high in helium-3, and this suggests that we have strong magmatic contributions to these fluids. Excuse me. So overall, we see there's a relationship between strain localization and magmatic fluid flow. So we can summarize part 1 of this presentation on this box diagram here. We have low S-wave velocities in the lower crust, likely indicating the presence of magma. We have swarms of mid to lower crustal seismicity. This potentially supports magmatic volatile release along fault and fracture networks. And although we cannot make this assertion based on geophysical data alone, we can make this assertion based on our CO2 degassing studies, which support the transport of magmatic CO2 along rift-wide fault systems. These faults exhibit fault parallel springs with magmatic fluid contributions, and these magmatic fluids rise through the rift in regions of high fault strain. Lastly, as our rift systems evolve and the location of highest strain migrates from the borders to the rift center, so too does the Okay, so I hope from that exercise that I've convinced you there's a correlation between magmatic volatile release and strain localization during early stage rifting. However, by necessity, these volatile transport processes are also linked with magmatic processes. So we're going to explore magmatism in a bit more detail now. In particular, we're going to look at the nature and distribution of faulting during the establishment of mid-crustal axial magmatism. And this is during the establishment of what we call these magmatic segments in our rift evolution model. So for this, we have a new focus site. It's the Takana Depression. So for your reference, the Natron-Magadi basins are situated here. So we're about 500 kilometers north of our previous site. And as we head north, we expect to see more evolved rift systems. And this is true in this case, but Takana is somewhat unusual and a little bit anomalous in the eastern branch. So firstly, the Takana Depression has localized right within a Cretaceous Paleogene rift, which predates the East African rift system. So consequently, the Takana Depression actually initiated in pre-thinned lithosphere. Also, the Takana Depression initiated early in pre-rift, in pre-thinned lithosphere. So syn-rift stratigraphy supports rift initiation at about 25 to 30 million years, suggesting this is one of the oldest zones of extension in the East African rift. Additionally, thermochronology support a phase of exhumation at about maybe 45 million years, although we don't really know how much rifting occurred there. So the point is that the Takana rift is actually slightly harder to fit into those evolutionary models I actually showed you earlier. But even with that in mind, there is still a lot that we can learn about how magmatism and climate affect rifting by actually examining this section of the rift. So the Takana Depression is unlike many other parts of the East African rift in that it's a broadly rifted zone, which I'm going to call the Takana Rift from now on. So here we have an annotated DEM of the region. We can see that the basin is segmented both to the north and also from west to east. These black lines show us the border faults that bound various rift basin segments in the Takana Rift. We've got the south and north Lokichar basins, the Takana Basin, the GEO Basin, and also the South Turkana Basin shown here. Additionally, rift-related subsidence in the Pleistocene helped to establish a closed basin lake, shown here in the blue, Lake Turkana. And Lake Turkana is about 50 to 100 meters deep. So the Turkana Rift also has an evolutionary history that's quite different to many systems in the East African Rift. And we can illustrate this by looking at the general structure of different basins and their timing of formation. So here we have a cross-section through southern regions of the Turkana Rift. These cross-sections are based on reflection seismic surveys and also boreholes from exploration that was conducted mostly in the 1980s. In each cross-section, we can see that there are 3 basins segmented across strike. So from Y to Y, we've got South Lokichar, GEO, and the South Turkana Basin. From X to X, we have North Lokichar, Turkana, and also the northern end of the GEO Basin. These gray regions in here show us our pre-rift basement, and these white regions show us the basin fill sediments, which in places can reach up to about 7 kilometers in thickness. Hopefully you can also see that this synrift fill thickens towards our border faults, suggesting that these border faults are the dominant control on tectonic subsidence in this region. So by understanding the ages of different sediment packages in these basins, we can elucidate the broad timing of rifting in each basin. So here I provide an example of one horizon to show this. So this is Horizon O. Horizon O is about 4 million years old, and it represents that sort of the top of this 4 million year old Gombe lava group. So this presence of this horizon actually gives us an idea of what was rifting before and after this 4 million year old layer was deposited. So if we look at South Lokichar, we don't see Horizon O in the basin. So this suggests that rifting occurred before 4 million years and also stopped before 4 million years. In the GEO Basin, we see Horizon O. This suggests that and it's quite shallow, which suggests that rifting began quite a bit before 4 million years and actually slowed down or even stopped sometime after 4 million years. And then in South Turkana, we see Horizon O at the base of the synrift fill. So this suggests that rifting in the South Turkana Basin initiated after 4 million years. So based on these kinds of relationships, this is the history of rifting in the Turkana Depression based on the study from Morley. So firstly, in the late Oligocene, we have rift initiation in the southwest, in the South Lokichar Basin. And what we see from here is that rifting slowly migrates both north and also to the east. So by the middle Miocene, the locus of rifting was encompassing all of these regions here, again showing us north and eastward migration. By the early Pliocene, the locus of rifting was mostly in the GEO and Turkana basins. And then from the late Pliocene to present, rifting has migrated even further east and has even now started to initiate in the South Turkana basin shown here. So hopefully from looking at this cross-section and the timing of evolution of this system, you can see that the Turkana Rift is different to those typical East African rift basins that I showed you in that model for the Eastern Branch. In particular, we have this wide rift with lateral basin migration rather than axial focusing in some of these basins. And perhaps the reason for this difference is that for at least the last about 20 million years, we haven't had significant magmatism or volcanism in the Turkana Rift. There have been pulses of flood lava eruptions, but then there have also been long hiatuses of millions to even tens of millions of years with little volcanism. So perhaps this pattern of rifting of Tucana in the past is more to do with a lack of magmatism. And with this point in mind, this brings us to our overarching question. Where is the locus of rifting today in the Lake Tucana Rift? And does magmatism play a critical role in driving modern rifting here? So to address this, we'll be focusing in on the South Tucana Basin. So everything that we look at from now on in this presentation will just be focused in this red area here. And the South Tucana Basin is also a great test case because it's different to these basin systems that I showed you to the west. These ones here. So specifically, it has a large Quaternary aged axial volcano. This is called South Island volcano. And a recent mount inclusion study by Tyrone Rooney shows that the likely Holocene age lavas at South Island were fed by a magma chamber at depths of about 12 kilometers. And this shows us that we likely have an active magma chamber below this volcano, and it's situated at depths that are quite similar to axial magmatic segments further north in Ethiopia. You can see some examples here for comparison, such as Kone, which has a very similar depths for its magma chambers. So by looking at the faulting patterns here, we can examine how magmatism may have impacted rifting in Tucana and whether it shows a similar style of magmatic rifting to these Ethiopian rifts. And we'll be looking at the South Tucana Basin through the lens of high-resolution single-channel seismic data, or CHIRP data. These seismic data were collected in 2009 to 2011 by my postdoc advisor, Chris Scholes from Syracuse University. You can see the position of the seismic lines here that we analyzed in our study. So here's an example of some of the seismic data. You can see the position of this profile line in yellow here. Please note that the depth on this profile is in milliseconds two-way travel time. So 100 milliseconds on this y-axis is equal to about 75 meters, and this section here is about 25 meters thick. Now, hopefully what you can see just from this image is that we have really high quality data producing a high resolution picture of the shallow subsurface. Here's an interpretation of this profile. You can probably see that it's relatively easy to follow our seismic horizons and also observe how they are offset when they cross faults. So this is a great data set for resolving fault histories across the width of this entire basin. Additionally, a lot of cores have been taken from the basin, each of these about 5 to 10 meters long. This one here, 46P, was used to build a radiocarbon age model by Morrissey and Scholes. So I'll quickly show you how this age model was produced. Here is core 46P. Like I showed you before, it's just northeast of South Island volcano here. This is approximately where the core would have sat in this seismic section here. And here we have the age model for this core, and it's built using the program Bacon by Bloor and Kristen 2011. We have depth along this core here on the x-axis, and we have our age on the y-axis. So what is this plot showing us? Well, at different depths in this core, materials were extracted for radiocarbon dating. These materials were things like ostracods, macrophytes, and organic rich mud. These smaller blue shapes show us the radiocarbon ages to 95% confidence. And the Bacon model utilizes those dates that I just showed you at different depths in the core to get a probable age path to 95% confidence. And from here, we can match our core ages to these ages to our core to get estimates of the ages of different seismic horizons. So from this analysis, we estimated that seismic horizon here, horizon 3 shown here, should have an age based on the core of somewhere around 10,000 years to 9,000 years old. So in all, we have all the necessary ingredients for a tectonic study in our region. We have high resolution seismic data, which gives us fault displacement information and a spatial distribution of extension. We also have age constraints. From the age model, we know that these two horizons here, horizons 2 and 3, about 9,500 years old and about 5,000 years old. We also have uncertainties on these, which I'll show you later. And because we have these age constraints, we can get rates of extension. And as I'll demonstrate later, we can also investigate temporal changes and rates of faulting. But firstly, we're going to look at the spatial distribution of extension. And we'll look at rates of extension across the whole fault population. And let's remember that we have some overarching questions. The question is, where is the modern locus of extension or rifting today in the Turkana Rift? And does magmatism play a critical role in this modern rifting? Okay, so what we did was, the first thing we did was map out seismic horizon 3 across the entire basin, right? So you can see an example of our mapping here on a profile line. And this is the 9,500-year-old seismic horizon, and we just map them out from all of our seismic lines. We then also identified rift normal faults based on how this seismic horizon was displaced in all of our seismic sections. And then we also measured throw along these faults, right, by taking the vertical separation between the footwall and the hanging wall cutoffs on every fault. So based on this mapping, this is a structural contour map for horizon 3 across the basin. So we have depth to seismic horizon 3 from the top of the lake, and this is in two-way travel time in meters per second. All you really need to know is that regions of the greatest tectonic subsidence are in blue, and regions of less subsidence are in red and yellow. And these black lines represent our faults. So what does this show us? Well, straight away, we can see that we have focused subsidence along the rift axis. And this region of subsidence aligns with South Island volcano. And also note that this pattern of strain is different to our older basins to the west, which were dominated by border faulting rather than this axial faulting, and also volcanism and magmatism were not heavily involved. We can also explore tectonic strain distribution further by looking at along strike patterns in the distribution of extension. Essentially, we can go from west to east along these different transects and sum the amount of throw on every fault we find along seismic horizon 3. This will give us the cumulative extension for every transect, and then we can actually examine along strike variations in extension once we've achieved this. So here are our results showing how much extension is accommodated along strike in the South Turkana Basin on our different transect lines. So on the x-axis, we have distance away from South Island volcano, getting further away from the volcano to the right of this plot. And we have total extension on the y-axis, and these error bars mostly relate to uncertainties based on fault. These plots show us that we're getting extension increasing towards South Island volcano, and we interpret that this suggests that we're having magmatic strain focusing around this volcanic center. And thus, in the South Turkana Basin, magmatism plays a key role in driving axial rift faulting. We also know the age of this horizon that we've been measuring. So we can get an estimate of the time averaged extension rate in the South Turkana Basin. And within about 10 kilometers of South Island volcano, we estimate extinction rates of about 3 to 5.8 millimeters per year across the Holocene. And these extinction rates are remarkably similar to extinction rates for this whole system based on GPS data, which range about 4 to 5 millimeters per year. So given the close match with the GPS and our geologic extinction rates, we believe the Holocene extinction in the Turkana Depression is focused in this region here at this latitude within the South Turkana Basin. Furthermore, about 80% of the time average extinction occurs along the rift axis here and aligns with South Island volcano. So all this rifting appears to be focused within a recently developed magmatic segment. And remember, this is very different to past rifting in the Turkana Depression, and it shows us how magmatism can change the nature of rifting and drive intense strain localization. Okay, so that is how extinction is spatially distributed in the South Turkana Basin. So next, we're going to take advantage of our age constraints and examine possible temporal changes in faulting. And in particular, in this last part, we're going to examine how fault behavior within the rift can be impacted by changing climate on 1,000 to 10,000 year timescales. So we're also going to stick with the Lake Turkana Rift and examine how climate-induced lake level change can impact fault behavior and rift development. So Lake Turkana, like many basins in the East African Rift, has a fluctuating lake level on 1,000-year timescales. So depending on regional climate across the continent, Turkana goes from high stand phases where the lake is overfilled to low stand phases where the lake is basically underfilled and is a closed basin lake. And all of this is dictated by climate across East Africa. And this is illustrated on this plot. Here we have the lake level curve for Lake Turkana from Morrissey and Scholes 2014. So we have time on the x-axis from the past to the present, and then we have lake level on the y-axis. Right, and this shows us that about 5,000 to 8,000 years ago, during the African humid period, Lake Turkana was overfilled, having a high stand, and then we had this climate change during the post-African humid period across East Africa, and the lake level in Lake Turkana dropped by about 100 to 150 meters based on this drier climate. And what we're asking the study is, what were fault slip rates like during the African humid period, where we have this lake high stand, and what were fault slip rates like during this low stand period when regional climate changed? And overall, we're asking, do we see a change in fault behavior resulting from this climate transition? So to show how we examine secular changes in fault slip, let's take this fault here as a possible example. So at this location, we can look at the throw accumulated on the fault on different horizons, which will be shown on the y-axis. We can also consider the ages of these horizons on the x-axis. So we know that horizon 2, which I showed you earlier, has an age of about 5.2 thousand years. So it sits here on this plot. If it has 3.5 meters of throw, right, we would plot a value somewhere here on this plot here for this horizon, for horizon 3, right? 5.2 thousand years and 3.5 meters of throw. We also know the age of horizon 3. It's about 9,500 years old. So it sits here on the x-axis. And if we have about 4.6 meters of throw on horizon 3, we put a second plot point on this plot, right, to represent this. So from these two plots, we can see that we have displacements on these different horizons that are different ages, right? But why do we care, right? So from these measurements, we get distance and time values on these plots. So the slopes of these lines between these points will represent slip rates on the fault during these different time intervals. However, there's one more caveat to these, and that's that these aren't exactly unique solutions because we have uncertainty with our inputs. So first we have age uncertainties, represented by this black line here. And this can be related to uncertainties from the radiocarbon ages, for instance. And then we also have throw uncertainties, which can be related to a possible range of different seismic velocities. So actually the true value of our throw and age rests somewhere within these boxes here. And this means that there's a possible range of multiple sort of throw time paths for this fault for our analysis. So to account for the possible range of throw time paths, we ran a series of Monte Carlo simulations using these age and throw constraints for these horizons. So here are the results for 1,000 simulations for this fault. Note that the fault has more than one possible throw time path. And based on the slopes of these lines, there is a range of possible slip rates, but some slip rates are more probable than others. Okay, so what do we do with this data? Well, remember that what we care about is the fault slip rates during and after the African humid period. So the slope of this blue line here gives us the slip rate during the African humid period, and the slope of the yellow line here gives us the slip rate after the African humid period. And if we subtract these two values, we get a change in slip rate after the African humid period. So for every fault, we subtracted these values for each of the 1,000 simulations to get a full picture of the probable changes in fault slip rates. So in all, we analyzed 27 faults at these locations here. So we ran 27,000 simulations of these potential throw time paths, 1,000 simulations for each fault. So here's an example of the results of 1,000 simulations for fault 10. This is a frequency histogram of fault slip rates. We have slip rate on the x-axis and frequency on the y-axis. Essentially, you can imagine these as probability density functions, showing you the probable different time average slip rates for our different time periods. In the orange here, we have the frequency distribution of fault slip rates during the African humid period. So this is the possible slip rates that could have occurred when the lake level was high. And in the blue here, we have the frequency distribution of fault slip rates after the African humid period. So this is a range of fault slip rates when the lake level actually was low and had dropped. So also remember that we can subtract these values to get changes in slip rate between these different periods. So this is the frequency distribution of the change in fault slip rate after the African humid period. So eyeballing this, we can see that this fault has an average change in fault slip rate on the order of about 0.25 millimeters per year. We're about 99% confident that this fault has experienced an increase in fault slip when lake level dropped in Lake Turkana. So in the interest of time, I'm just going straight to a summary of the results of our 27 analyses. Please don't spend a lot of time looking at this table. It just shows us the mean change in fault slip and the standard error of the mean. But overall, what we observe is that we get a mean change in throw rate for every fault of 0.18 millimeters per year at the end of the African humid period. So this may not seem like a very large change in throw rate, but we've got to remember that this is the mean change for 27 faults. So if we consider this change for every fault, we're actually looking at an increase in extension rate within the basin of more than 1 millimeter per year for the last 5,000 years when lake level was significantly lower. So in all, we see that lake level drops in Lake Turkana during regional climate change is accompanied by a significant increase in the rate of faulting. And usually I'll try to finish this talk by testing whether there's a causal effect, and I have some slides that do speak to what actually may be ultimately driving this change. But I see that I'm kind of out of time. I think it's 5:02, Catherine, so I imagine it's probably a good time to stop here. Would you think?
No, you can take your time. Like it's okay.
Okay. Oh, it'll only take a few more minutes. So I'll spend the next just 5 minutes just to explore how we looked at the potential causal effect for how this lake level drop may have produced this change in slip rate. So to examine whether these changes in lake level do drive changes in fault behavior, I've been working with Liang Xu, who has conducted numerical models of crustal stress changes associated with lake loading. So Liang has run a series of models using PyLith, and these can simulate the flexural isostatic response to water loading, and particularly the water load provided by Lake Turkana, which you can actually see here. This is this model run, and you can see how the water is loading our elastic crust here. Essentially, Liang can also track stress changes associated with this elastic response and also look at Coulomb stress changes in the vicinity of faults that he puts in his model, like these faults that we have here, faults 1 to 6. So Liang changed the lake loading in the model based on the lake level curve of Morrissey and Scholes 2014. So we can see that lake level curve, and I showed you this earlier. Shown here is this black line. We have the lake level values on the y-axis. And also, he's tracking the Coulomb stress changes related to this change in lake loading. And you can see those for our 6 faults shown here, right? We're getting this increase in Coulomb stress around these faults, ranging between typically about 100 and 200 kilopascals. So this is showing us that the elastic response to this lake loading is actually sufficient to enhance the rates of faulting during the post-humid period. However, magmatism may also play a key role in this too. So Liang has actually published a recent paper in 2023 that shows that lake level reductions in East Africa have the potential to enhance melting in the rift. So here's some model results from his paper where he's looking at basically the melt extracted compared to a baseline. So this blue line here is showing us the change in water mass in Liang's models, and this is the extra melt that was produced compared to his baseline runs. What it shows us is that as that water mass is decreased in the rift system, we're getting enhanced melting in rift systems similar to those like Lake Turkana. The other thing is this excess melting will result in more magma coming into the crust into things like axial magmatic segments. So in addition to modeling that elastic response to the lake loading, Liang's also modeled stress changes associated with an enhanced magma flux in the South Island magma system. So here Liang has modeled a 3-kilometer radius magma chamber with a depth and depth range that is based on those melt inclusions I showed you earlier from Rooney 2022. He then modeled the Coulomb stress changes associated with an enhanced magma flux of about 1.5 cubic kilometers per 1,000 years based on those other melt models I showed you earlier. And so these simulations also produce Coulomb stress changes around the fault systems. And interestingly, these Coulomb stress changes range between about 400 and 650 kilopascals and exceed the Coulomb stress changes related to just the lake loading or the flexural response to the lake loading alone. So in all, by comparing those two model runs, we conclude that changes to the magmatic system in response to climate-induced lake level fluctuations probably play the primary control in modulating rift fault behavior. And in all, this suggests that climate tectonic interactions are going to be enhanced within continental rift systems experiencing active magmatism. So I'll just finish off by throwing out a few broad conclusions that summarize the work here. So we see that we get significant volumes of deep CO2 that are released along rift-wide fault systems, particularly in our early stage rift basins. We see that magma and magmatic fluids are helping to assist rift basin evolution and strain localization. We see that climate change actually does have the effect of influencing rates of faulting across parts of East Africa. And lastly, climate tectonic interactions seem to be enhanced within continental rift systems experiencing active magmatism. So with that, thank you for listening, and thank you again for the invitation. And I'll be happy to answer any questions if people have them.
Thank you very much, James, for this fantastic array of observation. It's really great data and observations. Any questions? So either you unmute yourself or you put something in the chat, which I can read for you. No question?
Something popped up in the chat.
Yes, someone else put, okay. Thank you for the insightful presentation. In your work, you highlight the role of magmatic volatile releases in focusing strain. Could you elaborate on how these volatiles specifically influence the distribution of fault strain between borders fault and actual fault system? Are there distinct markers of signal that can help predict such behavior?
Yeah, so I don't talk much about the mechanisms, obviously, in the presentation, where our work is mostly focused on the spatial association. So, I mean, we can speculate. I mean, obviously that high fluid pressures can make it easier because it affects mean stresses that are being applied to faults. So that can help to mean that they can fail under lower differential stresses. Also, fluids can drive alteration that can make faults weaker and more prone to slip. So there's a range of possible sort of mechanical processes that can assist in it. So I guess our work is just showing that there's more to do with the spatial association. So where the fluids are more involved, the faulting appears to be more active on geological timescales. So that's kind of our marker that we're really looking at, is that spatial association. Now, there is more work that's being done in the Lake Natron region and the Magadi Basin regions, and so people like Miriam Rees has shown evidence in a lot of these axial regions that we're getting sort of these swarms of seismicity and pipe-like swarms of them, which might indicate sort of fluid migration through these active regions as well. So there are definitely potential seismic signals as well, but I'm not as involved in specifically looking at those active markers. Our work was looking at sort of geologic time and then trying to find our best links to it. I hope that answers it.
I would say so. Any other question or comments? Okay, so maybe I ask one. In fact, do we have any ideas or hints of why the eastern branch is magmatic and the western is not?
Yeah, this is definitely not the stuff that I've looked into in as much detail as a lot of geophysicists. One of the things that kind of stands out is position of that low velocity zone related to the African superplume.
Mm.
And it does seem to be sort of, if you look at its position relative to the Tanzanian craton, it seems to be somewhat offset and more sort of more pushed towards the eastern branch itself. And I get the feeling that may have encouraged significantly more melting in that region. I guess that's the best that I could really come up with. You know, it's just the position of that superplume and how it's deflected around the Tanzanian craton.
But the Turkana depression could not have modified, for example, create an anisotropy in the propagation of the rift north-south.
I mean, there's no reason why it's not possible. It's just in the east, in those eastern branch basins, you know, magmatism does appear quite early without much rifting or overall extension being required. So I feel that it's more bottom up than top down. That's just my thoughts on it, at least.
Okay. Okay. Any other question? Well, myself, I would like to thank you again, James, because you showed us a very excellent array of observations and meticulous work on the ground. So I think for all the modelers, it's amazing, amazing source of information. So thank you very much. Thank you. And and thank you everyone for coming today to our GEO@EAIFR webinar series. Thank you very much.